Okay, this is the third hour of Physics 1A for March 5th, May 5th. Okay, we're now going to look at some of the applications of rotational kinetic energy, and this is the first problem we're going to look at. So it says, an unwinding cable. We wrap a light, non-stretching cable around a solid cylinder with a mass of 50 kilograms and a diameter of 0.12 meters. It rotates on frictionless bearings about a stationary horizontal axis. So here's the axis, and it's rotating about this. We pull the free end of the cable with a constant 9 Newton force for a distance of 2 meters. It turns the cylinder as it unwinds without slipping. The cylinder is initially at rest. We want to find its final angular speed and the final speed of the cable. Does the problem make sense to everyone? So it tells us that it's a solid cylinder. So for the solid cylinder, we have to go and look at this table right here and be like, okay, where's the solid cylinder? Okay, here it is. Solid cylinder, rotating about an axis through its center, not through one edge or any other way, but through its center, which is what's happening. Has a moment of inertia of 1/2 mr squared. This is going to be one of the most common ones you're going to use in a lot of these problems. So the moment of inertia, I, is going to be 1/2 mass of the object times its radius squared. And we know in this case that the mass is 50 kilograms. We know that it says the diameter is 0.12 meters, as you can see on the picture. So that means that the radius r is going to be 0.06 meters or 6 centimeters. Okay, the other information we have is that we pull with the force of 9 newtons for a distance of 2 meters. So we unwind this this cable for a distance of 2 meters, and we do so with a constant force of 9 newtons. And we'd like to figure out what the final angular speed of this is, as well as what the kind of tangential velocity of the cable is at that time. Well, specifically, it says the final speed of the cable, but it's going to be a kind of tangential speed. Okay, so how can we do this? We just learned about kinetic energy. We're given this problem that has forces and distances in it. How can we figure this out? Yeah, we can use work, exactly, because we know that the work done by non-conservative forces is equal to the change in kinetic energy of an object plus its change in potential energy. Now, because the center of mass of this object is not moving, that means that its initial and final potential energies are going to be 0, or there's going to be no change in potential energy. It's not moving up or down. As far as kinetic energy goes, it's not moving, but I'm going to write down what this equation is going to start looking like from now on. This is awful. I'll start writing too many subscripts here. So when we talk about kinetic energy now, we're going to have translational kinetic energy and rotational kinetic energy. And for the translational kinetic energy, what we're going to care about is the final velocity of the center of mass of the object and the initial velocity of the center of mass of the object. So I'll just write them like that. It's a lot of subscripts, but this means velocity center of mass final, velocity of center of mass initial. And we also need to include the new thing that we've included. If an object happens to be rotating, we're also going to need a 1/2 I omega final squared minus omega initial squared. Now in this case, it starts from rest probably, right? Yeah, it's initially at rest. So that means that omega initial is equal to 0, so we can get rid of that. Now on the left-hand side, we have work done by non-conservative forces. Is this pulling force non-conservative or is it conservative? Yep. So in this case, it's going to be, so this is a non-conservative force because the only conservative forces are spring force, gravity. Everything else is non-conservative, right? in this class. The electric force is also conservative. Okay, so that means the work done by the pull, I guess we could say, should be equal to all of this. And the velocity of the center of mass is 0 to begin with, and the final velocity of the center of mass is also 0. So what we have then on the left-hand side is just the force that we're pulling it at, which is 9 newtons. We'll just call that F. Multiplied by the distance that we pull it, which is 2 meters. We'll call that D. Is this going to be positive work or negative work? It's positive, yep. It's making the object speed up. It's increasing the energy of the system, so it's positive. And the displacement is to the left while the force is to the left, so they're pointing in the same direction. So there we go. We can now solve for omega final by saying 2 times F times D divided by I. If I take the square root of that, that should be equal to omega final. So this is going to be the square root of 2 times 9 newtons times 2 meters. And then we divide by the moment of inertia. Okay, so I haven't put this in yet, but it's 1/2 mass, which is 50 kilograms, times the radius, which is 0.06. And then we just square this. So omega final is so 2 times 9 times 2 divided by 0.5 divided by 50 divided by 0.06 twice. And then all of that's raised to the 0.5 power. It looks like it's going to be 20. So we get omega final is equal to 20 radians per second. We're not done because we also wanted to find the final speed of the cable. Now, when I have a cable that's going off in a straight line, it's going to pick up a tangential velocity that we can call Vt. And the connection between the rate at which the cable is peeled off and the angular speed is just the radius of the object multiplied by omega. Did everyone else get 20 on this too? Okay. So we take the radius, which is 0.06 meters, and we multiply that by omega, which is 20. And 20 times 0.06, probably, you'll see, it's 0.6 times 2, which is 1.2 meters per second. That's it. Anyone have any questions? Pretty easy problem. We will eventually start doing things that are a little harder, but we're starting with simple things and just slowly building. Okay, any questions at all about this problem? Alrighty, then we're going to do this one. Okay, I'll draw a picture for this one. I don't really like the book's picture for this one, so we're going to draw our own picture. Okay, it says, we wrap a light non-stretching cable around a solid cylinder with mass m and radius r. The cylinder rotates with negligible friction about a stationary horizontal axis. Okay, so let's start drawing a picture with this. So we have a cylinder, and we wrap some string around it. We tie the free end of the cable to a block of mass m and release the block from a distance h above the floor. So connected to this, we have, it's like a spool. So we have a rope coming off of here. Maybe we use a different color. We have a rope that's coming off of here, like this. And hanging from the rope is a box. And our box has a mass of m. And the cylinder has a mass of capital M. Okay. And the cylinder is free to rotate about a horizontal axis through its center. And it has a radius, capital R. So this spool right here has a lot of rope wrapped around it, and also we have the ground down here, where this box is a height h above the ground. Initially. And I think the whole thing starts from rest. It says we tie the free end of the cable to a block of mass m, and we release the block from rest at a distance h above the floor. As the block falls, the cable unwinds without stretching or slipping. You're going to see this type of language a lot. Okay. Find the speed of the falling block and the angular speed of the cylinder as the block strikes the floor. So this is our initial. And we'll make a second screen here for final. Probably make this picture way bigger than I need to. So let's copy this. Bring it over here. And then we'll just drag this guy down to the ground and make this longer. Okay, so there we go. So this is our initial, this is our final, and by the time the block hits the ground, it's going to have a speed, and right before it hits the ground, we're going to call that speed v final. We're going to say its initial speed right here is equal to 0. The initial angular speed of this is going to be 0, but by the time we get to here, it's going to be rotating, because the block is sliding down, so this thing has to start rotating now. And again, there's like an axis through this thing, so it looks like it's suspended in space, but the idea would be that, like, you know, there's a rod going through this that is supported in some way so it can roll. So our goal is to find what is v final and what is omega final. Okay. Do y'all want to try this one actually? Why don't I give you 5 minutes to actually try to do this one yourself? I don't do that enough. I usually do that in actual classes every time we do a problem, but I don't know why I don't do that so much more. So why don't you all try this? So basically, try to solve. I'll give you 5 minutes. You're going to use energy, basically. So at 4:38 p.m., we'll talk about this. Oh, and your answer is going to be symbolic in case that wasn't obvious. Oh, it's a solid cylinder, so the other piece of information that I should write on the screen is that you're also going to need to know the moment of inertia of the solid cylinder, which we just used it in the last problem, but that doesn't mean that you've memorized it. So, and we're using capital M, right? Okay. So it's 1/2 big M times R squared. That's the moment of inertia for a solid cylinder. Okay, just delete that answer somewhere, please. I didn't ask you to put your answers in the chat. Okay, I'll just delete it for you. Yeah, don't put your answers in the chat. Just try to solve it and we'll talk about it. It's okay. I didn't say don't do it. I should have said don't do it, I guess. It's my bad. You didn't know. Yeah, that was 5 minutes, I guess. It's probably a little less because I think that was like just turning to 4:34, but it's probably enough time. Okay, so let's talk about how to solve this. Hopefully most of you were able to get it during that time, but if you weren't, it's okay. So in this problem, again, we're going to use energy. We have an initial position and a final position. We've pretty much labeled everything. The one thing that I didn't label here is the y-coordinates. So what I'm going to do is I'm going to define this to be y equal to 0, the ground. So we'll call y final equal to 0, and we'll say y initial is equal to this height h right here. And that should give us all that we need to solve this. So we're going to use work done by non-conservative forces equal to change in kinetic energy plus change in potential energy. Now, this means that we need to find the change in kinetic and change in potential energy for the entire system now, because there's more than one object moving. So I'm just going to use, well, let's do that. So for work done by non-conservative forces, are there any non-conservative forces in this problem? Nope. There could be some friction at the axle, but it says negligible friction. So there's that. So then change in kinetic energy is going to be 1/2. Now, the bigger mass is not translating, but the little mass is. So I'm going to write 1/2 m, little m, times v final squared minus v initial squared. So that's the mass of the box. The box is not rotating, but the other object is. So we'll have 1/2 I omega final for the for the disk minus omega initial here, plus, now the big disk doesn't move, but the other object does, so we'll also have mg and then y final minus y initial. Just barely fit that in there. A lot of this stuff's 0, so we'll go through and define all the things that are 0. All of the initial velocities are 0, and the final height is 0. So I'm going to take the term mg y initial and move it to the left-hand side. So we'll have mg y initial is equal to 1/2 mv final squared plus 1/2 I omega final squared. Okay, now we have an equation that has, I mean, there's a lot of symbols, so I think sometimes it can be hard to differentiate between what's a symbol and what's like a given value. But in this case, I would say the masses are given, the mode of inertia is given, and the height is given. So we can plug in here mg times h. But we're still left with two unknowns then, even if I plug all this stuff in. So I can plug in the moment of inertia too if I want to. So this is 1/2 times I, which also has a half in it. This is what I was saying. Be a little careful about this. It's a really common mistake to just drop this half right here, because I think your brain just, like, you see the half right here and you just forget to write it. I do it too, so I totally understand if that's what happens. So that's the moment of inertia. Don't forget the half times omega final squared. But we're still left with an equation that we can't really solve now, because even if mass, g, h are given and r is given, if we had numbers for those, we don't know vf and we don't know omega f, right? Both of those are unknowns here and here. That's what we're trying to find, right? Find the speed of the block and the angular speed of the cylinder as the block strikes the floor. So what can we do? How can I relate this velocity, the velocity at which the block strikes the floor, to the angular speed of the disk? Yeah, we can use the v equal to r times omega equation. So we know that the tangential speed at which the rope slides off right here, right? When we say tangential speed, we're saying basically this speed right here. There's a tangential speed of a point on the disk, and that tangential speed is equal to the radius of the disk times the angular speed omega, in this case omega final. But the rate at which this point on the disk is going down is the same as the rate at which the cable is going down, which is the same as the rate at which m is going down. And all of this is because of the fact that it says as the block falls, the cable unwinds without stretching or slipping. That means these things are all connected to each other. If the cable was stretchy, if the cable was slipping, these things wouldn't be true anymore, but this is true because it's not slipping. So this is then going to be equal to the final speed of the block right before it hits the ground. So we can either replace Vf with r times omega final, or we can place omega f with v over r. It doesn't really matter which one, whichever one we want to. So just for not having to do a bunch of fraction stuff, let's replace Vf here. So this is going to be m times, so v sub f is now going to be r times omega final. This whole thing is squared, plus half times a half is a quarter. And now we can solve for omega final. And we're going to get that omega final is going to be equal to, so we'll just leave it squared for a moment. In the numerator, we'll have m times g times h, and then in the denominator, we're going to have 1/2 m plus 1/4 capital M, and all of this is multiplied by big R squared. And then if we square root it, we'll get an answer for omega final. So that's our final answer. And then if we want to find v final, we have this equation over here that says that v final is equal to r times omega final, which, if you notice, there's an r squared in the denominator right here that's inside the square root. So our answer for this is just going to be square root of mgh divided by 1/2 little m plus 1/4 big M. And those are our answers. Does anyone have any questions? Do you all find this stuff to be pretty simple? It's pretty straightforward. Does it make sense? Is it hard? This thing that we just did here is going to happen a lot in these problems, where you're going to end up with two different velocities, an angular velocity and a linear velocity. And this is just almost always what you're going to do, okay? Right, Kelvin, yeah, exactly. It's definitely not intuitive. But once you've seen it once, now your head should be kind of on alert that you're going to do this a lot. You're going to see this happen quite a bit in these kind of problems. Specifically, what we're going to see in the next chapter is what happens when you have an object that's like rolling along a surface. So it has both a velocity for the center of mass and it has a rotational speed, omega. It turns out that you can use the exact same relationship in that case too. Okay? Now, as we develop more ways to solve problems like this, we need new ways to describe what's happening. So the next topic, and this will allow us to solve much more difficult problems. These problems are pretty simple, to be honest, but they do like build, right? So this first one's pretty simple, 9.7 is pretty simple. It just teaches you how to use work with energy. Then this one adds in the idea that there's a connection between the tangential velocity and the rotational speed. So the next thing to do is to look at objects that are rolling, okay? And also to look at things like pendulums that have, or pulleys that have masses and how that affects motion. But to do that, we need to look at the connection between torque and angular acceleration. Okay. This is one of those things that I can derive, but it often doesn't really matter if I derive it or not. So I think it's better for me to show you how this works and then to use a problem as a way to try to help you understand what it means. So I'm just going to use the connection between linear and rotational motion. So in linear motion, we have Newton's second law, which states that the net force acting on an object is equal to mass times acceleration of the object, right? For rotational motion, we can actually now start to use kind of analogs to allow us to take a linear equation and turn it into a rotational equation, okay? We already saw some example of that earlier with the rotational kinematic equations. They are exactly like the regular kinematic equations, but they just have different quantities subbed in. So, if I want to talk about rotational motion, then I need the rotational version of force. What's the rotational version of force? Something we learned about really, really early on. That's right, torque. So if I replace the force with torque, which is a vector, what's the rotational version of mass? I, which is a moment of inertia, yeah. And then what's the rotational version of acceleration? We learned about this one today. It's alpha, right? So this is the connection between torque and angular acceleration. If I sum up all the torques acting on an object, it should be equal to the moment of inertia of the object multiplied by its angular acceleration. And technically, we could have solved the problem we just did using this equation right here, actually, by looking at the torque that's produced by the tension in this rope, figuring the angular acceleration of this object, and yeah. So let's look at a problem that we can solve with this, and probably the simplest version of a problem that we can do is this one right here, the Atwood machine. Paste. There we go. Yeah, this is a pretty good example of something where we can use torque and angular acceleration to make it to solve. Okay, so it says the Atwood machine shown is a solid uniform cylinder with a mass of 4 kilograms and a radius of 20 centimeters with a cord with a 3 kilogram and 5 kilogram block attached to each end, passing over the cylinder. Find the acceleration of each block and the tension in each cord. I'm going to draw a bigger version of this. So here is our disk, and attached to the disk we've got these two ropes. One here. One here. Which one's heavier? The 5 kilogram one's heavier, right? Okay. Attached to each of these we have blocks. So one right here, and one right here. I want to give these symbols. So I'm going to call this one M sub 1. We're going to call this one M sub 2. And this is going to be capital M. And it's going to have a radius R. This whole thing is suspended from the ceiling. So this is basically just a big pulley. And it's suspended from the ceiling like this with a rope. And the whole system is going to tend to rotate. So this object is going to rotate like this. This one's going to go down, and this one's going to go up because 5 kilograms is bigger than 3 kilograms. And let's write over here, M is equal to 4 kilograms. M1 is 3. And M2 is 5. R is 20, so 0.2 meters. And that's all the information we have. Our goal is to find the acceleration of each block and the tension in each chord, so there's 2 different tensions. Now to do this, we're just going to do what we've done in the past. We're going to draw free body diagrams for each of these objects. For M1, there's going to be a tension that goes up this way that we're going to call T1. There's also going to be a tension that goes down, or sorry, a weight that goes down. And the tension should be bigger than the weight. So that's going to be M1G. And we'll put a little dot right here to separate those 2 forces. So this is going to be M1 times G. It's going to have an acceleration upwards that I'm going to call A. For the forces that are acting on the pulley itself, there's going to be a tension force. And since it's going up on this one, it's going to be going down right here. So the same tension force T1 is going to show up right there. So that's T1. Moving over to mass M2. M2 is going to have a tension that goes up as well. We'll call it T2. The tensions in this case are going to be different from each other, mostly because the pulley has mass. If the pulley didn't have mass, the tensions would be the same. So that's going to be T2 right there. Technically, I need to draw it so that T2 is bigger than T1, so I'll try to do that on the next thing that I do. And then we're also going to have the weight of M2, which is pointing down. This, and this one should be bigger because it's moving down. So this is going to be M2 times G. And the acceleration of this object is downwards. Now, the disk is going to have an angular acceleration that we're going to call alpha. And one other force, we need to draw the forces on here. It's going to have a force T2 that goes down this way. What other forces would the disk have? Weight, yeah. So I'm just going to draw these freehand. There would also be a weight going down this way. And then it needs to have some kind of support force, right? We'll call it the normal force. All right, we're not going to need to use these in this particular problem, but... So there's all of our forces, and if I want to analyze this, we have to look at each object separately and write down equations for each one of them. So 2 of them are going to be really easy. So for M1, we're going to say net force acting in the y direction is going to be equal to M1 times its acceleration. I'm going to make this the positive y direction for this one. So that means we're going to write T1 minus M1G equal to M1A. For, we'll do M2 over here. For M2, we're going to define down to be positive y because that's the direction that's accelerating. And we're going to write sum of forces in that direction in the y direction is equal to M2 times its acceleration. There's m2g minus the tension T2 is equal to m2a. So we get those two equations. They have three unknowns, T1a and T2. So I need one more equation. So let's leave this one alone for now, and this one as well. We'll come back to them. The last thing we want to do is analyze the forces that are acting on the wheel. So on the wheel, or on the pulley, because its center of mass is not moving, that means the net force acting in the y direction on this object is going to be 0. That pretty much means that this normal force here needs to be big enough to support T1, mg, and T2. So N would be equal to this one plus this one plus this one. But that's not going to be particularly useful for us. It doesn't ask us to solve for this normal force. We don't need to write an equation down for it. But what we can write is for the pulley, or the disc, whatever you want to call it in this case. The whole point of this problem is just to analyze what happens when you have a massive pulley as opposed to a massless pulley. Because up till now, all the problems we've done, we've basically been dealing with massless pulleys, except for the one we just did, I guess, technically. So now what we'd like to do is to be able to say that the net torque that's acting on this disk is going to be equal to its moment of inertia multiplied by alpha. Now, it's a solid uniform cylinder again, which means we know that the moment of inertia of this object is also going to be 1/2 times big M times its radius squared. Like I said, this one shows up just a ton. So we need to sum the torques about some point. Anytime you sum torques, you need to define an axis of rotation, right? So let's define this point in the center. It's kind of the obvious point to choose to be our axis of rotation. If we choose that point to be the axis of rotation, and we make the direction of our angular acceleration to be positive, it's rotating like this, that means I'm going to define, what is that, clockwise is positive? Clockwise is positive. Then I have these two different torques. There's a torque produced by T2 right here, and a torque produced by T1. T2 is going to produce clockwise torque. What should I write down for the torque due to this force T2 right here about that axis? Yeah, T2 times big R, right? Minus, and that's because the distance to this force is R, and the angle between that and that is 90 degrees. Same thing over here, 90 degrees, so we'll have T1 times R, and this one's going to be negative, and this is all equal to I multiplied by alpha. We can factor R out. We'll have T2 minus T1 multiplied by big R is equal to I, which we said was 1/2 mr squared, times alpha. One of these R's will cancel. Now, once again, we have a new variable. We have, from the first equation, we had two unknowns, T1 and A. M2 added another unknown, which was T2. This equation has added yet another unknown, which is alpha. So, we have three equations. This one, and this one. But we only have four unknowns. Oh, sorry, but we have four unknowns. So we need one more equation. What's the other equation going to be? Alpha is equal to A over R. That's right. That's right. So early on, we said that tangential acceleration was equal to R times alpha. So all we have to do is say, is the acceleration that we have for M1 here and here, are these tangential accelerations? And they are, right? Because if I tell you that this has an angular acceleration of alpha, that means that the tangential acceleration would be pointing kind of like this. But with the way that these ropes are attached, the acceleration of the rope is going to be the same as the tangential acceleration of a point on the disk. So since acceleration is equal to r times alpha, we can just take that and plug it in right here, right? That's basically just A. So if we do that, we get T2 minus T1 is equal to 1/2 big M times A. Now let's just look at these three equations because I think that they're all kind of interesting. So first equation, pretty normal. We've seen this before. This basically says that the tension force is bigger than the weight, and the difference between those two is equal to M1A, right? The equation for M2 says M2G minus T2 is equal to M2A. Normal kind of things, like sum of forces is equal to mass times acceleration. But this equation's a little bit different, right? What it says is that if I take the tension on one side minus the tension on the other side, that's equal to not just the mass of the pulley times A, but there's a 1/2 factor here. Now, we know where the 1/2 came from, right? It came from the mode of inertia. But what I find interesting about this is that if you think about what Newton's law says, it says when you sum up forces, it's equal to, you take the mass of an object times its acceleration. It's like this is saying the same thing, right? It's like sum of forces, T2 minus T1 is equal to MA, but there's a half that shows up. So it's almost like, you know, the whole point of this problem is to look at what happens when you put a massive pulley into a problem. And it turns out that when you put a massive pulley that's uniform, so that all the weight is evenly distributed, it's almost like it contributes half of its mass, not its full mass, to affecting what's happening for the motion. Okay. Anyway, just something as an aside to think about. All right, I think we can add these three equations together, so I'm going to do that. It's probably the fastest way to solve these. So if I take this equation, copy, paste, if it'll let me. Move it down here. And this equation, copy, paste, and move it down here. I think we can add these three equations together. And just to indicate that we're doing something different, I'll make them all black. And we'll add these three together, not the ones above it, so just these three here. And what we'll get is T2 minus T2, which is 0, T1 minus T1, which is 0. We just have M2 minus M1 times G is equal to acceleration multiplied by 1/2 of big M plus little m1 plus little m2. And we can then solve for the acceleration, which is going to be m2 minus m1 times g divided by 1/2 of big M plus m1 plus m2. And that's the answer. We just need to plug in the numbers. Now notice that this reduces down to the result that you would expect. If you make the mass of the pulley, which was big M, if you make this 0, then you get the same solution you would expect if you had treated it as a massless pulley, which is good. So our answer now is, and you still see this 1/2 of the mass of the pulley showing up here in the bottom. Okay, so M2 is 5, so this is 5. Everything's in kilograms, right? So I'm just going to write 5 minus 3 times g divided by 1/2 of big M was... Notice, what happened to the radius, by the way? Did you notice that? The radius is just gone. It's just completely gone from our equation. That happens a lot in these problems, that the radius will just completely disappear, which is kind of interesting. Because this is the interesting thing about it. When you talk about mode of inertia, even though it's defined like this, and the radius absolutely matters, when you look at a lot of types of problems, it's actually not the radius that matters so much as it is this part, the 1/2 m, and really just the coefficient at the end of the day that matters. Which tells you that moment of inertia is more about shape than it is about like anything. Okay, anyway, so 1/2 of big M. What was big M? That must have been 4. Okay, so big M is 4. So 1/2 of 4 plus M1 plus M2 is 3 plus 5. And that's all equal to the acceleration, which is going to be, let's see, so this is 2 plus 3 plus 5 is 8 plus 2 is 10. 5 minus 3 is 2, so it's g over 5, which is approximately 2 meters per second squared. Did I do that right? Looks right to me. Maybe I made a mistake. I don't know. You can all tell me. kind of reaching the end of our time here. So we didn't really cover all the topics I wanted to this week, mostly because I just wasn't able to do a lecture on Monday, but we'll be fine. I actually have like 2 weeks set aside for, I think, gravity, so we're not going to need that much time. So we'll catch up what we missed up on next week. So the next question is, I'm gonna end the lecture now, but I'm gonna go check Mastering Physics and make sure that the homework assignments still sync up with what we're doing. But that's gonna be all for this week, and I hope you'll have a good weekend. I'm gonna stick around for the last 5 minutes of class and just kind of talk about the lab, though, just to repeat some things to make sure you're all